Okay, hi everybody. Today we are doing the integrals by residual theorem. The integrals that we are interested in will be in this type, px over qx. Obviously, qx will have some zeros on the denominator, and then the singular points will be obtained. And in order to handle this integral by using a residual theorem, okay, the degree of q, which is the denominator function, should be twice as much the degree of p. So if this is second order, this should be constant. If it is third order, then px can be first order equation, okay? And another condition that we have in order to be able to solve this problem is that the poles or the singular points should not be on the real axis, because the method requires that we draw some kind of semicircle and then increase the radius to infinity so that we cover all minus infinity to plus infinity. Minus infinity will be from this side and plus infinity there. So when we increase the radius, it means that we will have scanned all the region. Okay, so the singularities that are below the real axis will be excluded, of course. They will not be causing us any problems. Only the ones which are in this circle will be causing some problems. Okay? But these problems will be used as the advantage, of course, to solve this integral. So by using the residual property. So the first example that I will be giving is integral from 0 to infinity dx divided by x squared plus 1. X squared plus 1. So as you see, this integral is not from minus infinity to infinity, but because it's even function, in other words, when you change x to minus x, this denominator doesn't change any sign, so that the function seems to be even. So this can be written as 1/2, okay, from minus infinity to infinity. So this is the first thing you have to check to write the integral from minus infinity to plus infinity, okay? So, okay, let's check this. Okay, zoom in thing. Okay, so we have now this integral to take. What we do is this. Since z equals x plus iy, okay, z equals x plus iy, dz will be equal to dx. Because we have only dx here, and dx can be written as dz, because z is related to x. If this is so, then this function can be written as, okay, the integral is written as integral, okay, minus or closed curve c, dz divided by z squared plus 1. Okay, z squared plus 1. Hold on, please. Okay, so we have this. Now, as you see here, pz is equal to 1, but qz is just z squared plus 1, which is second order, and it checks we can solve this problem. Okay, we can solve this problem. So how can we do this? First, we write z squared plus 1 as, okay, z minus 1, z minus I times z plus I. Okay. So the function is written like that. Wait a minute. I hope that it will be clearer soon. Okay, so z minus I is the thing which creates a problem, because if you look at this complex plane, this is real axis and this is imaginary axis, and z equals I and minus I are here. Okay, so now the circle that we are considering with radius r includes only this singularity. So this is the only thing which has problems. So the residual is obtained by just multiplying the whole thing by this, getting rid of this, and calculating the rest of the function at z equals I. Okay, as you see, this is now if z equals I, 1 over 2I is the result. So now the residual, the 2 pi I times the residual, which is 1 over 2I, and as you see, 2I cancels, and then you get pi. But remember that we had here 1/2 here, right? 1/2, because we went from 0 to infinity to minus infinity to minus infinity. Okay, so in this case, the result will be just pi over 2. So 1 over 2 is there. Okay, so, okay, I see. Okay, hold on. I'll check the